Hello, it's me, Mr. Duffy again, and welcome to GCSE Chemistry Paper 1 Revision Part 2. Now, the first thing I can assure you about this video is it's much shorter than video 1. That was very content heavy because there was a lot more maths in this video. This covers topic 3, which is mainly moles, topic 4, acids, metals, electrolysis, and topic 5, exo and endothermic reactions. Anything in red is the triple higher only content. I just made one mistake in video 1 I want to correct quickly. When we were talking about the reactivity series of metals, I said sodium burns with an orange flame. I meant to say yellow. We all know sodium burns with a yellow flame. I hope you can forgive me. Okay, now let's move on to topic 3, moles and calculations. You're going to be using the play and pause button a lot here so you can see where I get the numbers from and perform the calculations. So quickly, here's your topic list. And we're going to go through all of these now. And it's really maths based. And I'm going to show you the keys with the maths today, okay? Practice, practice, practice. And eventually on exam day, it will just be an autopilot and you'll get the answers like a habit. Very, very important. So the golden rule is you must show your workings out, okay? If you don't show your workings out, you're at risk of getting no marks instead of full marks. It's all or nothing. If you get the wrong answer and there's nothing else on the page, they'll just give you 0. And in the pressure of an exam situation, it can make you have silly mistakes, okay? We're all human. We all can sometimes make mistakes, and the key is damage control. Instead of it costing you 6 marks, maybe it does cost you 1 mark instead. So if you take a look at the grade boundaries from 2022 to 2019, we can see around 9 mark difference in the bottom ones, okay? And I remember one student, his only goal was to get 3 9s in biology, chemistry, and physics. And then on results day, he gets a grade 7 in chemistry, and he's very upset, like he failed. So obviously we got his paper, got it rechecked, and he didn't do as I say. He got 9s in all his tests, but in the pressure of the exam situation, he didn't show his workings out. One question for 4 marks was to do with significant figures. He didn't do it to significant figures, got 0. Another was to do with titrations, and he missed out by 1 decimal point. So instead of getting full marks, he only got 1 out of 6, and that cost him from a grade 9 to a grade 7. Okay? So while I tried to console him, inside I was thinking, yeah, I kind of told you for 2 years, but obviously I'm not a mean person, so I didn't say it to him. Anyway, what about me? What would I get if I sat a GCSE exam? I'd obviously get a grade 9. I'm a teacher. In fact, if there was a grade 11 exist, I'd get a grade 11. But I wouldn't get 100%. Okay, I'd probably get 97, 98%. The reason I wouldn't get 100% is there might be some weird suggest question that I just don't have a clue of. Or I can also make a calculation error. I'm a human being too, so it's perfectly possible for everyone to make an error. Don't worry about it, but you must show your workings out, okay? Getting some marks is better than getting no marks at all. So here's just a bit about scientific notation, which we'll be looking at a bit today. Maybe you want to press pause for a bit of these, because we're going to be working with some very big and small numbers. Now, and we're going to talk about silly answers, okay? Like here's a silly answer, but it's kind of a joke. Another one. This one, it's 20,000 hertz, but I do like the answer, Mariah. 4 octaves of greatness, so I did like that answer. But actually, I'm going to get rid of my face now so you can see the slides properly. What I mean by silly answers are answers that don't make any sense because you've done the maths wrong. For example, calculating the size of a cell in biology, and you calculate the size of the cell to be 20 kilometers. As big as London, okay? That clearly is a wrong answer and shows you're not paying attention to what's going on. Or, what's the shortest safe stop distance for a runway for this plane to stop? And you calculate 13 centimeters. That's shorter than a ruler. Again, it shows that you're not really understanding what's going on. So we're trying to eradicate them mistakes today. And I'm going to show you with a positive attitude that you can do this if you follow my instructions with scientific notation. So here's the key calculator skill. 4.7 billion, that's 4 by 0.7 by 10 to the 9, divided by 2.3 by 10 to the 5, that's 230,000. Immediately, I'm thinking 2 divided by 4 is kind of going to be 2. And then 9 and 5, that's 10 to the 4. So I'm looking at around 20,000 in my head just from a quick mental calculation. And when I go to do it, I get this ridiculous answer: 204 quadrillion, 347 trillion, 826 billion, 86,957. That's clearly not correct. Where did I go wrong? Here's the key point. You must use brackets when you are dividing with scientific notation, okay? That is how you get the right answer. I said it should be around 20,000, and it is. And I would like you to practice dividing. Always put the scientific notation in brackets, or else mathematically you are just dividing by 2.3, then multiplying by 500,000, and that's why you get a ridiculous answer. So brackets is the key. Another exam tip is this: you might get a long number on your calculator, but you're not going to write out the long number on your exam paper, but keep the long number on your calculator screen, because that will give you the exact answer in the marking scheme, okay? For example, this round up to 7.66, but keep the long number on your calculator screen. So let's get it all started, okay? Step 1, relative formula mass. It's really, really easy. You just have to add. You add the top numbers, the mass numbers of the periodic table. For example, look at nitrogen and oxygen on the right. The relative formula mass of nitrogen oxide, NO, is clearly 14 and 16 and 30. It's that easy. You're just adding them. So play and pause while you'll see some examples here. Nice and easy. Use brackets when you have to multiply. Getting a little harder, but use brackets when you need to multiply and you'll get the answer. And here's a really hard one that requires 2 slides. So the phosphate weighs 95, and then you add it to the copper, okay, because there's 2 phosphates, 95 times 2, to get 280.5 for copper phosphate. Now, you might want to play and pause here while we do percentage by mass. What does percentage by mass mean? It means what percentage of an element is in a compound. Here's an example. Calculate the percentage of carbon in carbon dioxide. Well, the molecular mass of carbon dioxide is 44. 32 plus 12. 12 divided by 44, 27.3%. Here's some other examples. Glucose is 180. The 6 carbons weigh 72. 40% of glucose is carbon. And here's another example here. Let's make sure you can follow the numbers. And we move on to the mole. The key point of topic 3 is the mole. So what is the mole? The whole point of the mole is it converts the periodic table into grams. One atom is tiny. Even in the tiniest substance, as you saw, like a grain of salt in the first video, there's still trillions of molecules, so we need to bring it to the real world. 1 mole is 6.02 by 10 to the 23. You need to remember that number for your exam. It's 602 billion trillion molecules. It's just a ridiculously huge number. So it turns the periodic table into grams. Okay, if you want an idea of how big that number is, just pause. Here's how many iPhones 1 mole of iPhones would be. Given that the Milky Way galaxy is 100,000 light years across, it's like 5 of our galaxies. 1 mole of iPhones will be the equivalent of 5 galaxies across. It's just insane. Okay, there are 3 types of matter: solid, liquids, or gases, and we're going to be doing mole calculations for all 3 of them now, okay? So first one is reacting masses, and that uses our classic number of moles is equal to the mass given to you in the question over the molecular mass of the element or compound. So here's some examples. 0.12 grams of magnesium reacted to produce 0.2 of magnesium oxide. When I subtract them 2 numbers, I get 0.8, okay, and then the molecular mass is 32, so there you go, 0.025, that is your answer, okay. Next, play and pause while we go through some more of these. Copper, 63.5. This gives me how many atoms. I multiply by the number of moles, and I get 2.28 by 10 to the 21. So 3 significant figures. Here's another one. Pay attention to the significant figures for 4 marks. 2 significant figures, 180. And now, reacting masses, okay? So very often you have to use the same equation twice. You find the number of moles on the left, and I get that as 0.00197. And then I rearrange the equation for mass on the right-hand side for zinc. Mass is number of moles times molecular mass. 0.0197 times 65 is 0.128 grams. As you can see, there is no ratios here. We're going to get into harder ones with a ratio. And in case you're wondering where the 254 came from, well, that's 127 times 2 for iodine. Here's another example. You might want to press pause and play here. Make sure you understand where the numbers come from. Again, no ratios in this. Again, no ratios in this. The molecular mass of iron sulfide is 152 when you do the calculation. It's the same question every time. Look at the way I do it. I do it the exact same way every time. Iron chloride is 162.5 when you do the maths and the relative formula mass. Now, if the question is in tons and the answer is in tons, you don't have to multiply, convert tons to 68 million grams. You can just keep it as it is. But it's the same question every time. Here's another one. And so you should be playing and pausing these and make sure you know where the numbers come from. So a typical person has a blood glucose concentration of 5 millimolar. That's 5,000th of a mole. What mass of glucose is in a typical person with 5 liters of blood? Step 1, number of moles is equal to mass over molecular mass. I rearrange that equation for mass. Now 5 millimolar is 0.005 moles. The molecular mass of glucose is 180, so that's 0.9 grams in 1 dm cubed or 1 liter of blood. And there's 5 liters of blood in a person, so in every person there's roughly 4.5 grams. In the pictures you see these kind of things that the diabetics use to check their blood sugar. That's what the 5 means. It should be 5 millimolar. If it's high, it'll be higher than 5 millimolar. If it's low, it'll be lower than 5 millimolar. Next, as higher level students, they'll probably ask you questions with ratios, which involves one extra step, okay? So as you can see here, there's a 3:2 ratio in the question, okay? Calculate the minimum mass of chlorine gas needed to produce 200 grams of iron chloride to 2 significant figures. Step 1. Number of moles is mass over molecular mass, 1.23. I then must divide that by 2 and multiply by 3 to get 1.846 for the chlorine, and then multiply by the molecular mass of Cl2, which is 71, and you'll get your answer as 130 grams to 2 significant figures. So pause this, make sure you see where all the numbers come from. And we're going to go through a few examples now where you should just be pausing and seeing where the examples come from. Here's a 1:3 ratio, and it's continued on the other page. So that's a 5-mark question for that one. Not bad at all. Here's another example with a 2:3 ratio, and they want your answer in milligrams, so you're going to get an extra mark for that. Easy. Multiply by 1,000. That's another 4-mark question. Find the number of moles of gold. Divide by 2, multiply by 3, and then multiply by 71. Okay, excellent. Now we're on to solids and liquids, okay? So, they sometimes ask this, number of moles is equal to concentration times volume by a liquid. But for these type of questions, you have to do one extra thing, and that is divide by 1,000. Because we work in centimeter cubes in our school lab, but the unit of concentration is a liter, but so you must divide by 1,000. I'll show you some examples now. So a student made 250 centimeter cubed of citric acid of 0.05. Calculate the mass of citric acid. The molecular mass of citric acid, I just do that myself, is 192. Step 1, number of moles is equal to concentration times volume over 1,000. I do that sum and I get 0.0125. I then get my molecular mass equation, number of moles is mass over molecular mass, rearrange it, and then multiply by 192 to get 2.4 grams. Here's another example. 0.048 times 250 over 1,000 gives you 0.012. Again, take your molecular mass equation, rearrange it, and you will get 1.08. Here's another example, exact same thing again. Just play and pause, make sure you understand where the numbers come from. And here's another example, exact same thing again. I hope you're getting the idea that I do the things exact same way, so it's repetition till it's a habit. And more examples. Make sure you can follow these with your calculator. Now we're on to solids and gases, and this will be asked a bit less frequently, okay, about gases, but they still come up a bit, okay? So here's a diagram of a gas, and the key point is this: 1 mole of any gas takes up 24 liters of space, okay? And the key is at room temperature and pressure, because obviously the volume of a gas will change if I go up or down in pressure. So if you want to have a rough idea, it's around the volume of a fridge, around 24 liters, okay? Maybe a bit more than that, a bit less than that, okay? So play and pause here so see, make sure you can follow these questions. Calculate the volume of 150 kilograms of chlorine gas. Okay, well, number of moles is mass over molecular mass. And because they want it in moles, I do have to convert the kilograms to grams this time. And I get 213 moles multiplied by 24, and you get 50,704 liters. That's the volume of 150 kilograms of chlorine gas. This next question here asks you, at 20 minutes, what was the volume of chlorine gas? Calculate the amount of moles. Well, let's have a look here. At 20 minutes, I see there is 6.5 grams, or 6.5 centimeter cubed. So I'll just do this. Number of moles is 6.5 divided by 24, 0.27 moles. It wants the answer in standard form, so it's 2.7 by 10 to the minus 1. Here's another equation with a ratio this time. So divide by 2, multiply by 3, and then multiply by 24 at the end to get 9. And in this one here, it's a 4-mark question, basically because you have to convert megajoules to 58 million, the kilojoules 290, and then you have to just multiply your answer by 24. That's an easy 4-mark question. And here's another example that combines finding the molecular mass with also finding the volume. So on to limiting reactants, okay? Unless you are the greatest chemist in the world, okay? Or not this type of chemist, I hope, but unless you're the greatest chemist in the world, you are not going to get A and B to match perfectly. You'll always have a little more of one reactant than the other because, you know, there's trillions of atoms, okay? Now, for a chemical reaction to occur, A must collide with B. Well, what happens if I run out of B? A is just going to be left on its own. So B was the limiting reactant, so it ran out first, and A, you say, is in excess. Here's an extreme example. 840 grams of carbon were burned in 96 grams of oxygen. What was the limiting reactant? Well, I know off the top of my head it's going to be oxygen, but I'm going to prove it mathematically. I find the number of moles of both ways. Number of moles is mass over molecular mass. I got 70 moles of carbon, but only 3 moles of oxygen. That means once the 3 moles of oxygen are used up, there'll be 67 moles of carbon left over. The oxygen is limiting, the carbon is in excess. Here's another example. 690 grams of sodium was reacted with 100,043.7 grams of chlorine. What was the limiting reactant? And this one has a ratio as well, so we'll just be clear on that one. Step 1, Find the number of moles of sodium, 30 moles. Step 2, find the number of moles of chlorine, 14.7. And then I'll deal with the ratio. According to the ratio, I would need 15 moles to fully react, but I only had 14.7. Therefore, the chlorine was the limiting reactant. So you might want to play and pause for a couple more of these examples. Get the number of moles of iron, number of moles of bromine. So it is clear from this that the iron is a limiting reactant, okay, because it is clearly in excess the bromine. Here's a real life exam question. Show that aluminium is a limiting reactant and it's got a ratio. So you find the number of moles of aluminium, the number of moles of iron oxide, 0.037 for aluminium, and you get divide by 2, multiply by 3, 0.0185. But you had 0.0188 moles, so therefore the aluminium is the limiting reactant. Here's another one with titanium chloride and sodium, exact same thing again. 40 divided by 190, 0.21. 20 divided by 23, 0.87. Then I do the ratio and find out I'll need 0.84 sodium. But I have 0.87, so I have more than enough. So therefore the titanium chloride is limiting and the sodium is in excess. Now we're on to percentage yield and atom economy, and it's pretty much all about making as much money as possible, okay? Percentage yield is very easy, actual over theoretical times 100. So here's an example here. 28.2 over 36 times 100, 78% is the percentage yield here. Here's another example, very easy. And another example, you might want to play and pause your way through these. Very easy. Again, always the same. They might get you now in harder questions for 4 marks here to rearrange. Okay, 92.3%. Now, I personally just convert to 92.3 to a decimal 0.923, but whatever way you do it, okay, if it's 92.3, your answer should be very close to 13.5 kilograms, and 12.4 is pretty close. Here they're looking for the actual theoretical mass. So I divide by 92 to get 13.59. Why percentage yields are never 100%? I love asking this question, okay? Sometimes the reaction is reversible. You learn more about that in topic 6, paper 2, where the products turn back to the reactants. Some of the product is lost when it is separated, if you don't filter it properly or you spill some. Or there might be unexplained side reactions that you don't know that are going on. Again, that will mean a lower yield. Now, atom economy is the same stuff. Okay, everything is made from atoms. Stuffs are made from atoms. Atoms cost money, and it's using them efficiently. Okay, so atom economy is the molecular mass of the desired product over the molecular mass of the total product on the right hand side. So as you can see here, I have 28 for carbon monoxide and 6. That is 34. And the desired product is hydrogen. That's 6. So 6 over 34 times 100 is 18%, 17.6% when you round it up to 18%. Here's some other examples here. 95 and 18 is 113. That's the total mass of the product. 84% is the atom economy. And if you have only one product, by definition, the atom economy is 100% if you've only one product. They've asked that a couple of times as a trick question. So you might want to play and pause through a couple more of these atom economy questions from real life exam papers. Make sure you get the same answer as me. And that's it. That is moles. That's topic 3, quantitative chemistry, done. Now on to topic 4, acids, alkalis, your metals, and your electrolysis. And titrations is the only thing that is on the not on the combined paper. Okay, the rest is. So firstly, acids and alkalis. You know your acids. Okay, and here's some examples of bases. A base is there's a solid version, and alkalis when it's dissolved in water. So you have the pH scale, which we use to measure how acid or alkaline something is, and we use this thing called universal indicator, which is red in acids, green in neutral water, and goes to blue or purple in alkaline solutions. So we're going to look at neutralization reactions when an acid and an alkali make a salt and water, and you've already looked at this when we made copper sulfate crystals in topic 1. The ionic equation for neutralization is the hydroxide ion reacts with the hydrogen ion to form water, and it's called neutralization because water has a pH of 7. So here's the one you did before, and you need to be able to predict which ones will make what salts, as well as working backwards. Now, titrations, this is triple higher only, so if you're doing combined, just skip forward to after this part. But the key is, what is the concentration of the solution? That is the key question in titrations. So you have this general thing of the pH scale. There's a burette and a conical flask. I'll talk about it in detail now. So you might want to play and pause while I talk through how you do a titration. Okay, here's a general diagram showing you adding the 25 centimeter cube with the pipette. You add a few drops of indicator. You add the thing, acid or alkali, to the burette, and then you let the burette into the conical flask. In this case, we were dealing with an acid in the conical flask because it's colorless, and a base, an alkali, in the burette that turned it to pink because it's phenolphthalein, the indicator. In all experimental write-ups, remember the tips. Say what you were measuring and how you were measuring it. We measured the time with a stopwatch. We measured the volume with a pipette. As long as you say what you were measuring and how you're measuring it, you will get the marks. So why do we use a pipette? A pipette measures a fixed volume accurately, and a burette measures a variable volume accurately. That's why we use these two pieces of equipment. Give 2 reasons why a burette is used. Measures a variable volume accurately, and you can add it drop by drop to get a very accurate endpoint. So here's the color change from colorless to pink. You might have seen that, but you would see it a lot better if you put it on a white tile. If you have your conical flask on a different colored surface, you mightn't see the color change as well, so we put it on a white tile. So, describe how the student would complete the titration. You might want to pause here and have a quick read through this. You definitely swirl it as you add it from the burette to make sure it mixes properly. And you repeat till you get 3 concordant results. Results within 0.1 centimeter cubed of each other. Again, press pause, read your way through this. And this is a real exam question. Suggest 2 improvements. Swirl the solution, there's no mention of that. And using a white tile, there was no mention of that. Titration maths. Students seem to hate titration maths, but they're not that bad if you just follow the formula and follow the routines, the practice. I have every titration question maths pretty much has ever been asked here for you, so it should soak in. So we use this formula, number of moles is equal concentration times volume because we're dealing with a liquid. In this case, we do not have to divide by 1,000 because you just end up multiplying by 1,000 at the end, so it's pointless. So step 1 is the way I always do it, is I write VA for the volume of acid, CA for the concentration of acid, and then VB for the concentration of base, and CB for the concentration of base at the side. Now I know it should technically be VA and CA because they're alkali, but you can't distinguish them, so I just write B for base. Now, I then look at my question, and you will get 3 of the 4 of them, and your job is to find out what the missing one, in this case, the concentration of the acid. Step 1, I find the number of moles of the base is 2.72. I then take that equation and rearrange it for concentration, and 2.72 divided by the volume of the acid gives me 0.544 moles. In this particular example, there is no ratio. You are probably going to get asked one with a ratio because you're in higher level students. So follow me here and write. Exact same thing again, lay out everything on the side, what I know from the question. In this case, I'm looking for the concentration of the base. Step 1, you find the concentration of the acid by multiplying those two numbers by each other. Step 2, you look at the ratio in the question, and it's a 1 to 2 ratio. So I multiply 0.72 by 2 to get 1.44. And then I take the equation and rearrange it for concentration. Here's another example. In this case, I'm looking for the concentration of the base. So if you take a look at the left, here's where the numbers come from. 13.3, 0.05, and 25. And it's the same thing again, but it's a 3 to 1 ratio this time, so I multiply it by 3, and again, rearrange my equation, and I get that answer. Here's another example with a 2 to 1 ratio. So 15.5, 0.5, okay, 0.0, 0.5, and then 25. I'm looking for the concentration of the base. There you go. In this case, it's looking for it in moles and grams, so this would have been a 6-mark question. We'll do the moles part first, okay? We did it. And then number of moles is mass times molecular mass, 0.62. And you will get the, I think this is, remember I mentioned the student earlier on, I think this was the question that he messed up on. He only got 1 out of 6 marks because he didn't show his workings out. He wrote 0.062 instead of 0.62, so he clearly multiplied by 0.05 instead of 0.5. Okay, show your workings out. They might sometimes give you results and you have to pick the ones that were in 0.1 of each other. They're called concordant results. I don't know why I wrote concurrent there. Concordant is the word. Again, same thing. Ratio 2 to 1. It's the same time every year. The mean of these is 12.13. Same thing again. Follow where the numbers come from. And again, calculate the mean, find out the concentration of the base. It's the same question every year, and this is every titration question that has ever been asked. Just make sure you go back and forth to make sure you understand where the numbers come from. Now we're on to strong and weak acids, and this is for everyone, including combined students. So welcome back, combined students. Okay, so a strong acid is one that fully ionizes in solution. That's like hydrochloric acid. And a weak acid is obviously one that doesn't fully ionize. Most of it stays as it is, like vinegar. So this is fully ionized. It's just a one-way arrow. Fully ionizes an aqueous solution for the full marks. That's strong. Here's a list of some strong acids. As you can see, they all contain hydrogen. Here are the 3 main ones on our course: hydrochloric acid, nitric acid, and sulfuric acid. Weak acids do not fully ionize, and you're going to see this reversible reaction symbol. This is more from paper 2. But 99% of ethanoic acid doesn't ionize, so therefore it is a weak acid. So explain why an acid can be strong but dilute. It is strong if it fully ionizes in solution, but dilute if there is only a small amount of acid per unit volume. If you only put a tiny drop in, it can still be strong and dilute. So here is an example. 1 gram of hydrochloric acid put in a litre of water would be a dilute solution of strong acid. Effective acid strength and reactivity, it's pretty easy. The stronger the acid, the more reactive it will be. So you have this kind of like strong acid, weak acid territory. Neutral is water at 7, and then going from weak base to strong base. So the pH of a strong acid is 1 because it's 100% ionized, whereas the pH of ethanoic acid is only 3, and the pH scale goes up in 10. So a pH 2 is 10 times stronger, or 10 times less strong. pH of 3 is 100 times less strong, 10 times 10. Next, we are on to the reactivity series of metals. So here are some common metals: aluminium, copper. Probably shouldn't have put brass in there because that's actually a compound, but the rest are elements. Okay. Now, here is the reactivity series of metals, and you can kind of split them into 3 categories. The really reactive ones on your course end in IUM. Not all metals that end in IUM are really reactive, but as far as your course goes, they are. Okay, so you might want to play and pause while I go through these. Displacement reactions and ionic equations. I have to revise what we did with the halogens because this is all about redox reactions. Okay, so remember, in this case, the chlorine, it was reduced, it gained electrons, and then the iodine is oxidized, it lost electrons. Now, we did this in our previous video, so just look over it quickly again. You can press pause. Now, in displacement reactions in metals, a more reactive metal will displace a less reactive metal from a compound, and you also need to be very aware of carbon. It's not a metal, but it is also used to displace metals from their oxides. So here is copper sulfate. Okay, iron is more reactive than copper, so it will displace the copper. And you can often see this with a color change. For zinc, it's colorless. Iron sulfate is light green, copper sulfate is blue, and aluminium sulfate is also colorless. So if I add iron to copper sulfate, it will displace it, turning the blue copper sulfate solution into iron sulfate, which is green. That's what you would observe, a blue turning to green. You need to know the ionic equation if you're doing higher. Okay, the oxidation state of any element on its own is 0, so iron on the left is 0 and copper on the right is 0. The sulfate copper is +2, -2, +2, -2. So here's your half equations. The iron is oxidized, it has lost 2 electrons to become positive, and the copper is reduced, it has gained 2 electrons to become copper metal. So the overall ionic equation is there because the charge of the sulfate ion does not change. So if you add zinc to copper sulfate, okay, zinc sulfate is colorless, you will see it go from blue to colorless, but not the other way around. Here's the ionic equation for that one. Just make sure you can follow that. It's the exact same thing again. And finally, metal extraction. Okay, we get our metals from mining them from the earth, okay, but they are mainly combined with oxygen, which is by far the most common element of the earth's crust. 46% of the earth's crust is oxygen, and we don't want our metals now. Rust is specific to iron, but we don't want our metals to be oxidized or a bit rusty. There are 3 categories. 1, unreactive metals. These do not need to be extracted because they are unreactive. They do not combine with oxygen. That's like gold and platinum. So here's like an old thing from the pharaohs in Egypt. That's gold, 3,000 years old, still in perfect condition because it's unreactive. Next category is metals less reactive than carbon. They are extracted by heating with carbon. The more reactive carbon displaces the less reactive metal from its oxide. And that would be a list of the metals there you can use by heating with carbon. Just basically anything that doesn't end in IUM. This is why carbon is in the reactivity series. So, as you can see, the lead had oxygen and it doesn't. It is reduced and the carbon gains oxygen, that's oxidized. Now, that is more foundation level. Higher level students need to talk in terms of electrons. The lead, okay, is reduced. It gains 2 electrons to become 0, and the carbon clearly is oxidized. It has lost 4 electrons to a charge of +4. Okay, hematite is the main iron ore iron is coming from, and it's quarried. People, you hear the word quarry, here's what a quarry looks like. It's where we mine ores from. Now, here's just a question they asked, a positive impact, a negative impact. Look at the marking scheme. Positives provides employment, improves the local economy, improves transport. None of this is on your course, it's more of a suggest question. Negative impact, definitely destruction of habitats, more pollution, fewer plants and all that. Now you might want to play and pause while I go through some of these ionic equations for extracting metals. Carbon oxidized, iron reduced. So the ionic equation is the exact same as the halogens, so I'm not going to spend too much time on it. So, an ore contains a metal, it is extracted in stage 2. Why does it need to be separated? Okay, well in stage 2, as you're going to see, it's not just pure metal, it's 70%. You have to get rid of the other 30% impurities that aren't the ore itself. Okay. Give one reason why cast iron isn't suitable for pylons. Cast iron is actually pretty brittle. And in step 2, most cast iron is converted into steel. How is it steel? It is allowed to react with oxygen. The carbon reduces, it becomes carbon dioxide. State 1 property that make aluminium more suitable than copper for overhead cables. Aluminium will probably be a low density, it's light. How can you tell that copper is a transition metal and aluminium is not? It's because it's group. Aluminium is in group 3, whereas copper is in the middle transition block. Copper can be extracted from solutions of copper salts by adding iron. Explain why. Iron is more reactive than copper, so we'll displace it. Pretty easy. Now we're on to metals more reactive than carbon. How do we get rid of the oxygen? We have to use electrolysis. Now I know students struggle with electrolysis, but it isn't that hard if you keep going over it, okay? It's actually one of my favourite subjects. So what's the problem? Why do students find it so hard? I don't know, but I'll try and explain it clearly. So, metals, pause here, metals more reactive than carbon. Heating with carbon won't work. Electrolysis is used. What is electrolysis? It is the decomposition of ionic compounds using direct current electricity. And here is the electrolysis of molten sodium chloride, and it has to be molten so the ions are free to move. You have 2 graphite electrodes there in black. The negative one is the cathode and the positive one is the anode. The way I remember it is A plus for anode. Electrolysis will not work in solids as the ions are not free to move, carrying the charge. They like asking that question. It only works in liquids or aqueous solutions, like where you dissolve the salts in water. So here is an aqueous solution of sodium chloride, or a molten solution where you just melt it. Now, here's the half equations, okay? The sodium gains 1 electron at the cathode, it is reduced. The chlorine, now you have to double it up because all the halogens are diatomic. So you have to double everything up to make Cl2 gas. So 2 chloride ions lose 2 electrons to become chlorine gas. So you should see chlorine gas forming there. Here's another one with magnesium chloride. It will gain 2 electrons, and the chlorine, the same thing again, it's oxidized. Here's the case study. They love aluminium, and I love aluminium. I even wrote it a love letter once. I love aluminium so much, okay? So first of all, what is an ore? An ore is a rock or a mineral containing enough of a metal to make it worthwhile to extract, and bauxite is the main ore of aluminium, okay? For example, if a 1-ton rock contained 1 gram of aluminium, that's not worthwhile. You need loads of aluminium. You can really see the aluminium coming out of this ore right here. So step 1 is mining the ore. We've already, like a quarry, we've talked about the environmental consequences of that. What percentage of the earth is aluminium? 8% of the earth of the crust is aluminium. That's pretty nuts to me, 8%. You wouldn't think it, okay, but 8% of the earth being aluminium, that's a lot. Okay, that's a huge amount. How much? 400 billion trillion tons of the stuff. Now, if only it were that easy to get our hands on it. Unfortunately, aluminium is very reactive and loves combining with oxygen to form aluminium oxide. And the whole point is we need to reduce the aluminium oxide, get rid of the oxygen, okay? Why is this difficult? Because it's very strong ionic bonding. The Al3 plus ions and the 3O2 minus ions, there's a very strong electrostatic attraction resulting in a very high melting point. So the first thing we do is lower the melting point. Aluminium oxide has a very high melting point, over 2000 degrees, due to its strong ionic bonding. There is also strong electrostatic attraction between these Al3 plus ions and O2 minus. In order to lower the melting point, it is first added to another ore called cryolite. Cryo means cold in science, and this lowers the melting point to 900 degrees, saving energy. Do not say saving money. While that is correct, it gets you 0 marks. You must say you added cryolite to save energy by lowering the melting point. Once it's lowered, we then use electrolysis, and it's set up like this. The walls are graphite. The walls are the cathode, they're negative, and in the middle is the positive anode, okay? So what's actually happening here is, why does aluminium metal form along the walls of the container? Well, as you can see here, the Al3 plus ions are free to move when it is molten. They are attracted to the negative cathodic walls due to their electrostatic attraction, and then you get 2 marks for the last point. They are reduced to aluminium metal as follows, and always give the half equation, okay? Always. Here's what happens to the oxygen. Again, you have to double up because of O2, so 2 oxygen atoms lose 4 electrons to become oxygen gas. Now, why is the positive electrode used up in this? Well, why must it constantly be replaced? Well, it's because of the oxygen gas formed. Remember, the electrodes are made of graphite, and graphite is made of carbon. So the oxygen reacts with carbon to form carbon dioxide gas, and this gradually causes the erosion of the electrodes, so they need to be replaced. Here's a rough drawing I did. Again, here's what it would look like in an exam. Why do the aluminium ions collect at the negative electrode? Because of their electrostatic attraction, they're positively charged. Explain why the electrodes are made of graphite. They've asked this before. Graphite has delocalized electrons, which means it can conduct electricity. Graphite is relatively inert. It's pretty unreactive. I know it reacts with the oxygen, but it takes a long time. And finally, graphite has a very high melting point. We're very often dealing with molten solutions of 1000 degrees, so our electrodes better not melt or it won't work. Now, the electrolysis of aqueous solutions, not molten solutions, when we dissolve something in water, okay? So here is the overall idea. Rather than using lots of energy to melt the metal oxide from a solid to a liquid so the ions are free to move, why not just dissolve the solids in water so the ions are still free to move, and that would save lots of energy and lots of money? Well, you can't do that, and the reason is this. If a metal is less reactive than hydrogen, it can be extracted from its aqueous solution. Unfortunately, copper is the only common metal less reactive than hydrogen, so for the rest of the metal oxides, you can't dissolve them in water, you must melt them, and that requires lots of energy. That's why hydrogen is in the reactivity series, and as you can see, most metals are above hydrogen except copper. But you do need to know the electrolysis of copper sulfate, so I'll talk to you about that now. Here's a more detailed view of the ions involved. I have copper ions being attracted to the negative electrode, and you can kind of see a brown layer of copper metal forming. I have hydroxide ions being attracted to the positive electrode, and I'll show you the half equation. You're going to see oxygen gas forming, and don't worry about the sulfide ion, nothing happens, and the hydrogen ion stays in solution. So here are the half equations you need to know about the electrolysis of copper sulfate. The copper gains 2 electrons, it is reduced to copper metal. And the hydroxide ions, I know it's a bit of a long, complicated one, but it is oxidized. It loses electrons to form oxygen gas, water. Okay, so you need to remember those half equations. What would you observe? Well, you would observe the blue, it would turn colorless because of the copper ions are being discharged to copper metal. Okay, you'll observe it being colorless. So the blue copper sulfate solution will become a paler shade of blue to colourless as the copper sulfate is electrolyzed. A layer of copper metal will coat the cathode, you'll see that. And finally, you will observe bubbles of oxygen gas will start forming at the anode. That's because the hydroxide ions are being oxidized. Here's just basically a general question that some of the copper felt did not stick to the electrode but fell to the bottom. Well, it will be insoluble, so you just use filter. You filter it out. Just have a quick read of that. Just use filter paper and you'll be absolutely fine. How can you conclude it's directly proportional? These are all straight lines through the origin, so they are all directly proportional. Now, you might want to play and pause while they ask about the electrolysis of brine, salt, water. So brine is really salty water with a lot of sodium chloride in it, okay? So explain the fate of the ions in the diagram, including any equations. Now, sodium is clearly more reactive than hydrogen, so it's going to stay in solution. The hydroxide ions also stay in solution, so let's go step by step. Step 1, the sodium ions stay in solution as they are more reactive than hydrogen. Next, the hydrogen ions, well, 2 H plus ions are reduced at the cathode to hydrogen gas. They gain 2 electrons. There's the half equation. Let's take a look at the chloride ions at the anode, the positive electrode. 2 of them will become chlorine gas. You've seen that plenty of times before. And finally, the Na plus and OH minus ions, they start joining together to form sodium hydroxide, which is an incredibly useful substance. 70 million tons of sodium hydroxide are produced annually. That is a lot, and it's mainly used in cleaning products. So that's topic 4 done. Chemical changes. We're nearly there now on to topic 5. This is pretty quick. Exo and endothermic reactions, okay? If you're doing combined, you just need topics 1 to 3. If you're doing the triple, you need the cells and the fuel cells as well. So in exothermic reactions are reactions that give off heat. Endothermic reactions are reactions that take in heat. Most reactions turn out to be exothermic. So you need to be able to draw these energy level diagrams. In an exothermic reaction, the energy of the reactant is above the products. And you need to be able to label the activation energy as well. And in an endothermic reaction, the reactants are below the products and the activation energy goes right up to the top. You need to be able to draw them. Here is a common exothermic reaction, the combustion of methane. And every chemical reaction needs a spark. That's the activation energy that's needed to start the chemical reaction. Okay, so that will be a spark from a lighter. Okay, so in the combustion of methane, okay, the bonds are broken. And then they are reformed to carbon dioxide and water. Bond breaking is endothermic, and so bond forming is exothermic. For example, here's the equation of respiration. This is what we do in our bodies, getting energy from food. And here is photosynthesis. They are the exact opposite of each other. In the reactants and the products swap position. So the energy change. You sometimes get asked about energy changes. Because the reactants and products are exactly the opposite, the energy change is also exactly opposite. It is exothermic for respiration, minus 2814, and it's endothermic for photosynthesis, plus 2814. Equal and opposite gets you the 2 marks. Now here you have to practice drawing them, and they'll give you some scaffolding to none. Here I just have to label B as the activation energy, only 1 mark. Here I had to draw and label the activation energy and the energy change, so that's 2 marks. Here, same thing, 3 marks though, because I had to draw the product line myself, okay? But 3 marks for that isn't bad. And here's another one for 3 marks. Make sure you're comfortable with these. Okay, here's clearly an endothermic reaction, okay, and you're asked to explain the shape of the graph in terms of the energy place. And it said I should use data from the graph. If you don't use data from the graph, it's one of the most common mistakes you to make. You're not going to get any marks. So The temperature decreased from 16.8 to 11.6. That's from 0 to 1.5. After that, that shows it's a endothermic reaction, and above 1.5, it increases to 12.1. Why does it increase? Because the reaction is complete, meaning that it will just naturally increase the room temperature as it takes in the room's thermal energy. Finally, bond energy calculations. Bond breaking is endothermic, bond making is exothermic, and that decides whether a chemical reaction is exo or endothermic. We'll take a look at the combustion of methane, and they do like this one with alkanes and bromines. The test for alkanes, this is topic 7 chemistry, but let's have a look here now at some bond energy calculations. So each bond has its own unique energy, as you can see, and you'll be given these numbers in your exam, and it's all to do with just the nature of the covalent bond. You can clearly see that a double bond in carbon is stronger than a single bond in carbon. That's common sense. So you must be able to identify what bonds are formed and where. So if you look from left to right, I see 4 CH bonds and 1 C bond and 1 Br bond. And then on the right, I see 4 CH bonds and 2 CBr bonds. And so I do the maths. Just spend a moment, make sure you can get that, and I get minus 93, proving it's an exothermic reaction. Here's another example. Just pause it and see that you can follow the numbers. So on the left hand side, 4 times 3 is 12 NH bonds. Here's another example. Make sure you can follow the numbers. Just pause it. And now they're asking me a kind of algebraic one here where I have the answer and I have to solve for x. So just follow me all the way down. Reactants minus products. So I keep x until I'm left with solving for x. Spend a moment looking at that. I know it's not the neatest, but you should be able to follow the numbers. Here again, they want you to find the bond energy of bromine. Again, this is like solving for x, okay? I'm going to call the bromine bond x and do the exact same thing. And I get that the bond energy is 193 at the end. Just follow the numbers by pressing pause. And it's true. The bond energy is 193. I figured that out mathematically. Okay, we're nearly on to our last topic now, electrodes and the reactivity series. Did you know you can make electricity without a battery? What are you talking about? Well, if I have 2 different electrodes, we're not talking about graphite here, we're talking about metal electrodes, they can be used to produce a potential difference and allow current to flow as long as I have an electrolyte where the ions are free to move. Okay, so here's copper and here's magnesium. They are 2 different reactivities, so they will cause a potential difference between them for electricity to flow, as long as there is an electrolyte where the ions are free to move. This is sometimes seen in putting different electrodes into lemon juice and turning on the light bulb. You might have seen that experiment before. So, different metals have different affinities for electrons. By using different metals in the reactivity series as their electrodes instead of graphite, a potential difference can be formed, causing electricity to flow without a battery. The bigger the difference in reactivity, the bigger the potential difference, the more current will flow. So as you can see, magnesium and copper will have a large potential difference, so we'll get a lot of electricity, whereas zinc and tin have a small difference in reactivity, so we'll get a smaller potential difference and a smaller current. Okay, you can't use really reactive metals like sodium or potassium because the electrodes will just explode. So just in case you're wondering why they're not there. Okay, so finding the reactivity series is just all about comparing the potential differences, okay? As I can see here, zinc has the highest voltage, it's the most reactive. Okay, copper is the least reactive, and then tin at 0.48 was in second place. Here's another example with iron. And as I can see, with the negative voltage, tin and lead are. So the higher the voltage, the more positive, the more reactive, and so on. If suggest to control variables, you control the concentration of the electrolyte and the temperature of the solution if you're doing that experiment. Here, put these 6 in order of reactivity. Well, magnesium is clearly the most reactive at 2.71. Next, I'm looking at cobalt with 62. Then nickel 59, iron, tin 48, copper 0, and finally silver has got a negative voltage. It will be the least reactive. And that's the answer right there. Justification: the higher the voltage, the more reactive the metal. Topic 5, fuel cells. Okay, how do they work? First of all, it is hydrogen reacting with oxygen to form water. It is not a combustion reaction. It's not rocket fuel, or basically cars would be flamethrowers. It's a redox reaction. By combining hydrogen gas with oxygen, okay, you produce water, and since the only product is water, it's considered a clean fuel, although, as we're about to see, there are some catches to that. So, how does a hydrogen fuel cell work? First of all, to notice is that the anode is now negative and the cathode is now positive. That is the opposite naming to electrolysis. Same with a battery. The anode is a negative in a battery, the cathode is positive. So you pump in hydrogen gas and the hydrogen is oxidized. It loses electrons and that forms an electron current, and eventually it is reduced at the cathode to water. So if you just pause for a moment just to read in detail what happens. But if basically the hydrogen is reduced and provides the electrons. So it has an anode, an electrolyte solution so the ions can move in a cathode. Hydrogen gas is pumped into the anode where it is oxidized, and that provides the electric current to power the car. And at the cathode, this is the equation, it is reduced to form water as follows. The only thing needed is to keep pumping in hydrogen to generate the current. So the advantages of hydrogen fuel cells is the only waste product is water, so there's no greenhouse gases like carbon dioxide or acidic gases like sulfur dioxide. And if the hydrogen was obtained from seawater, it is renewable. However, there are disadvantages. Hydrogen is an explosive gas and must be stored at high pressure, so you need a strong, heavy tank. If the hydrogen is obtained from methane, then it is not a renewable resource. And if the electricity for the electrolysis of seawater to get the hydrogen comes from the combustion of fossil fuels, you are still indirectly increasing greenhouse gas emissions. Sometimes they say you're just moving the problem from the filling station to the power station. Here's another diagram showing the reduction and the oxidation. And here are the half equations. Again, you do need to remember these as triple higher students. Now, finally, comparing electric cars versus hydrogen cars. Okay, fuel cells, okay, they're pretty clean, they're batteries, but cobalt is a toxic metal, and very often children have to mine cobalt for these batteries, okay? The Democratic Republic of Congo has the #1 source of cobalt in the world, and there's a lot of human rights violations going on there, okay? So batteries in electric vehicles are rechargeable, but eventually the battery will need replacing, and they often store less energy, so you have to recharge them more often. Why can a rechargeable cell be recharged? The chemical reaction is reversible. Give two factors that affect the voltage produced by a cell: the type of electrode and the type of electrolyte and its concentration. Balance the half equation, just double it all up. And why is it described as an alkaline fuel cell? Because the electrolyte was usually potassium hydroxide or something with hydroxide ions as an electrolyte. Okay, Electrolysis and chemical cells. Electrolysis uses electricity to produce a chemical reaction, while a chemical cell uses a chemical reaction to produce electricity. The commonly asked question. And that is topic 5, energy changes done. We're nearly there, we're nearly at the end. I just have one more thing to say to you, and that is exam technique. Okay, these are some key tips for your exam. So you might want to go through these quickly. You have a rule, and it is to get as many marks as possible, with the golden rule as a minute a mark. Read the whole paper first. They give you 5 minutes to do this, okay? If you've learnt off a 6-mark experiment, for example, and you see it, why not do it first and get it out of the way, rather than keeping the other 4 in your head if they're not going to be on the test. You gain time on the math questions. A 6-mark math question doesn't take 6 minutes, so you have time to spend on the longer questions. And don't spend too long on suggest or evaluate questions. They're only worth 1 or 2 marks, and balancing equations are only worth 1 mark. If you get them, great, but if not, move on. Some students spend too long on these questions and run out of time. For example, suggest 2 possible problems with storing mud. Well, I'd say if the dam bursts, the houses will get damaged, but I can't for the life of me think of a second reason. I just can't. And I'm not going to waste time on it. It's only worth 1 mark. Don't waste time. Though if you wanted to know the answer, there it is. But I would have only got the dam bursting. I wouldn't have got the other ones. Answer the question that asks. Okay, for example, describe what you observed during the electrolysis of copper sulfate solution. And a student gives this perfect answer with all the half equations and gets no marks because they have not answered the question that they were asked. Unless you've got the best eyesight in the world, better than any microscope, you did not see the electrons being added onto the copper. Okay? What you did see is the copper turning from pale blue to colour. That's answering the question. That's the observation. And you also saw the copper layer form along the negative electrode, the cathode. That is going to get you the full mark. So answering the question that is asked. If they tell you to use data from a graph or table and you don't use any numbers or data, you'll get no marks. They've asked you to use data. You must use data from the graph or table. So many times everyone can see the line goes up. You must say at what point, okay? And finally, you do not have to do the paper linearly. Question 1, 2, 3, 4, 5, 6, 7. You can do it in any order you like. The last question might be your favorite, but if you run out of time because you do it linearly, you might lose out on marks. Okay, so you don't have to answer the questions in order. Do your favorite questions first. But every single year, without fail, you ignore, as soon as they say start your exam, everyone just turns over their page immediately and starts with question 1 and doesn't read the paper. You've got plenty of time. They give you 5 minutes. Please, please, it is a key tip. Do your favorite questions first. Get as many marks as possible. You don't have to do it linearly, but everyone always does. Anyway, that's GCSE Chemistry Paper 1 Revision Part 2 done, which means it's all done. So thanks for sticking with me. Okay, I know I said the video would be a bit shorter, but it's kind of the same time. But well done, everybody, and I will see you for physics. You've got this. I really believe in you. Take care. All the best. Nice one. Bye.